it's important to consider, and this is an extremely important issue, that the highest your structure and the highest is the impact of the structure, the environmental impact. And even more important, the highest is the induced risk of flooding upstream. It's clear that if you build a barrage, you increase the water level. This is what we want. But it's also clear that we increase also the flood levels. And the higher the structure, the higher the increase of the flood levels. So this is a verification that we need to absolutely make. Once that we build a structure over a river, the local, regional and national administrations, depending on the importance of the structures, ask you to verify the impact on the flood levels. This is extremely important. And what do you need to verify this impact? You need an estimation of the flood flow, and you need to typically apply a computer model to estimate the flood level after the intervention. We don't, again, we don't focus on the models for estimating flood levels. They are flood routing models. They are based on the application of the de Saint-Venant equations. They are typically studied in the subjects of fluid mechanics. So we don't study them. It's a side issue in our context. But the key message that I want to deliver to you is that an essential design variable for any structure that is interfering with a river is the flood flow. For a given return period, I think you already know this term, what it means, return period. It means the frequency with respect, the frequency with which a flood is expected to occur. So again, the key message that I want to deliver to you is we are learning today that any structure interfering with a river needs, as a design variable, also the flood flow. So we are learning today that this is another fundamental background that we need. I'm not sure, I have a lecture really on the estimation of the flood flows. I'm not sure whether we will have time to focus on it, because this is not an high priority for us. Our priorities are others, are the estimation of water resources availability, are how to design these structures, but this key message that you need the flood flow, it's important. Please retain it, okay?
I have just a question. So these structures are built and then verified for the flood?
Yes.
Or there is a process through which you can take into account the flood while you are designing?
No, typically what you do is you base our design on the design variables related to water resources management, and then you verify against the flood flow. And of course, you have to take into account before while designing some rule of thumb. And one rule of thumb is, in any case, the structure should not be higher than 15 meters, and the volume upstream should not be higher than 1 million of cubic meters. Typically, these structures are 6, 7, 10 meters high. 10 meters is usually a maximum, and then you try to remain within this range. And also, while you are designing, you should have a perceptual look upstream. You should understand if upstream there are flooding problems. So if there are urban settlements, urban areas, if there are other activities, human activities or roads that could be flooded, and if you see that upstream the risk of flooding is really low, then you are allowed to design a structure that is higher, and especially if the geology allows you to do that. If you realize that upstream there is already quite a risk of flooding because you had floods in the past, then you want really to keep your structure the lowest possible that you can make it. And sometimes there are structures that are the environmental flow spillway is just a couple of meters or even less higher than the riverbed. In this case, the effect on the flood flows is not very relevant. Because, you know, the effect on the flood flows of a structure is typically less relevant with respect to its effect on the low flows. And this is understandable because if you, during the low flows, the water level typically in a river is very reduced, like 1 meter. And then if you increase 1 meter, it's a significant increase. In flood flows, you have a water level that is 10 times higher, and therefore an increase of 1 meter is not very relevant. But still, there are these rule of thumb that you need to consider, and then once that you completed your design, you are required to provide a proof that the effect on the flood flows is negligible. Okay, so with these considerations, we fix the elevation of the environmental flow spillway. Okay, and then what is the difference in elevation between the environmental flow spillway and the diversion spillway? There is a fundamental requirement. We cannot get any water until the environmental flow passes through the environmental flow spillway. What happens over a spillway? Over a spillway, if you don't have any water, you have a dry spillway. Okay, perfect. And then let's suppose that some water starts coming from upstream. And let's suppose that here, upstream the structure, it's empty, it's dry. Okay, water starts accumulating against the structure. And then when water reaches the level of the environmental flow spillway, we start seeing some flow moving downstream. Good. If we get more water from upstream, the water level in the pool increases, and therefore the water level over the environmental flow spillway increases as well. Which means that the flow, the environmental flow increases, because over a spillway, if you have an increase of the water level, you have an increase of the flow over the spillway. This is quite clear. If water continues to increase the flow from upstream, we observe a continuous increase of the water level in the pool and over the spillway, and we observe a corresponding increase of the flow, the environmental flow through the spillway. At a certain stage, we will reach, finally, the desired value of the environmental flow over the spillway. When water is at that level, I can start diverting some water, not before. Therefore, and I will repeat this, the elevation of the diversion spillway should be the elevation of the water level which guarantees that through the environmental flow spillway I have precisely the environmental flow. So water increases its level because there is more flow coming from upstream. At a certain level I get, through the environmental flow spillway, the desired environmental flow. At this level I place the diversion spillway. Okay, so let's compute this elevation difference. Let me go back to the web page. And let's look at this. Sorry. Let me log out, because if I don't log out, it's just 1 second. Here we are. Just 1 second. We went too far away, but I don't see where is. Because by enlarging the view, it's difficult for me to get oriented. Let me see. Ah, okay, that's fine. Sorry. Here it is. Okay, so let's look at this equation. It's not easy, but I can do this. Oh, very good. Let's look at this equation. What is this equation? This equation, which you should learn by memory, is the formula for estimating the flow through a weir. And this is studied usually in fluid mechanics, and it can be demonstrated very easily by applying Bernoulli's theorem. Okay, so what can we see here? We can, this formula basically says that the environmental flow through the spillway depends on several variables, including what is called here H2, delta H2. What is delta H2? Is the elevation of water over the spillway. So basically, I'm not sure whether let me see if I can use the blackboard, because I don't feel comfortable without the blackboard. This is a bit technical. If I don't have the blackboard, I don't feel comfortable. Okay, so this is a spillway, very easy. This is a spillway, this is a cross-section of a spillway, and the flow over the spillway is occurs in this way. And we have, in the proximity of the spillway, we have a lowering of the water profile, because basically the spillway calls water, and therefore the call of the spillway implies a lowering of the water profile. So the flow over the spillway, which is Q dmV, we will see later how this is estimated, but this is, let's assume that is known. The flow over the spillway depends on the elevation of the water over the spillway. Delta H2. This is to be measured upstream. So basically this delta H2 is measured between the elevation of the spillway and the elevation of water upstream in the undisturbed position. It's understandable that if you increase the water level, you increase also the flow of the spillway, and also it's understandable that the flow over the spillway depends on the width of the spillway, which is here indicated as LC. therefore, if you look at the independent variable, there is delta H2, which we already discussed, the width of the spillway, again delta H2, and G is gravity. And also there is a flow coefficient, μ. It's a reductive coefficient which takes into account loss of energy over the spillway and other issues. It's determined μ is equal to, for a larger crest weir. This is a large crest. This is the crest of the weir. It's the top of the weir, and you see that it's long, meaning that it's large. For a large crest weir, μ is equal to 0.385. This is also called, the large crest weir is also called Bélanger weir. You may have also a sharply crested weir, which means that the crest is sharp, and this is called Bazin weir. But for river barrages, we usually use the Bélanger weir, and μ is 0.385. Please remember. Okay, so again, this relationship says that the environmental flow is given by the product of μ, Lc, width of the weir, delta H2, water elevation over the weir measured with respect to the crest of the weir, and upstream water level before the coal, multiplied by 2g gravity, again delta H2. So basically you could write this as Q dmv is equal to μ Lc g at the power of 1/2 delta H2 at the power of 3/2, 1.5. If you don't like the square root symbol, you can use powers in this way to avoid the square root symbol. Okay, keep in mind that here in this relationship, the width of the weir Lc is usually fixed a priori. And there are minimum widths that are imposed by the law, maybe imposed by the law. Usually it's about 1/2 meter. Therefore, Lc is decided a priori. Qdmv is known because we assume that it's known, and we will see how to estimate it. It's the environmental flow, which depends on the behavior of the river, and it's prescribed by law. So it's the law that tells you, I want a specified value of the environmental flow. It's known. μ is known, Lc is fixed. What is missing here, the only unknown is delta H2, which is the elevation of water in the pool, in the upstream pool, that guarantees that we have the environmental flow over the environmental flow width. And therefore, it is this level where we place our diversion weir. We put it here. Good. So delta H2 is our purpose, what we want. Good. Now, we still have to solve the design problem of fixing the elevation of the main spillway. But the concept is the same. We use the same relationship with only a change of variable. Now we have here the design flow, QP, the amount of water that we want to withdraw, and LP, which is the length, the width of the diversion weir. And of course we have a different elevation here. So, if this is the level of the diversion flow, we measure delta H1 here, and here I have the main spillway. This is the level of my main spillway. This is main, I hope you can see it. Yeah, you should see it. Main spillway. Good. Everything is clear? You see that I drew this shape of the main spillway, and I'll explain you why in a moment. Which is a gradual, you see that there is a gradual connection between the main spillway and the riverbed. And downstream here, I have my boulders to prevent erosion. Okay. So we solved the problem of placing the elevation of the different weirs. And now let me go back to the other problems. Design of gravel and sand traps. Everything of what I'm saying is described with some more details in the web page. For preparing your exam, please make reference to the web page. Okay? What is there is what I ask. Typically, when I sit in front of you, I look at the web page in order to better remind what I did, and this is my reference for deciding the questions. It's also, I also adopt this strategy because it allows me to make sure that there is an equal treatment for students attending the lectures and students that are preparing the exam offline. So you should make reference to the web pages, and there are everything of what I'm saying is there, and maybe a little bit more. If you find something more, please assume that I may ask it. And again, the web pages without links are what matters. Okay, so let's now focus. And there are some rule of thumb. First of all, what is design based on technical procedures here is the length of the sand trap. And then the length of the gravel trap is decided basically on a rule of thumb, like 1/3, half of the length of the sand trap. First thing. Second thing, the height of the submerged weirs, which divide the gravel trap from the sand trap and the sand trap from the tank. Okay, the height of these weirs is typically 50 centimeters. not more than 1 meter, because otherwise it becomes impossible to clean, to flush the sediment out. If you accumulate 1 meter of sediment, it's too much. 50 centimeters is fine. And when they are filled up, you need to flush. Okay? And another rule of thumb, the velocity of water in the centra is definitely less than 1 meter per second. It should be between 0.2 and 0.5. Let me see what I wrote here. Okay. Okay. Let me see, I think it is here. I can't find it. I'm sure that okay. The range which I'm suggesting here is 0.05, 0.15 meters per second. So I said 0.2, 0.5, it's a bit lower here. Of course, this is a rule of thumb. So I would say that if it is 0.3 is fine, but still, the lower the better. And this is why, let me go back. And this is why, the reason is that if the water flow is slowed down, the sand trap is more efficient. Okay. And then what we have to design is the width and the length of the sand trap. So basically, what are the relationships that you should use? First, keep in mind that there is a relationship that applies, that I think we already discussed, that applies to a current of flow. The water flow is equal to the product of the transversal area of the flow. Transversal area means you already know what is a cross-section. It's perpendicular to the velocity vector. And the area of the cross-section of the flow is the transversal area times the velocity of the flow. And we said that in the sand trap this is fixed in the range 0.05, 0.15 meters per second. And in the sand trap your flow is equal to the design flow, QB. And therefore, basically, you have already here a means to estimate the transversal area of the sand trap. And if you assume that the water elevation in the sand trap is about no more than 1 meter, the sand trap cannot be very deep because you need to get the sand to collapse to the bottom of the sand trap. If it is 3 meters deep, the sand has to travel for 3 meters in the vertical direction. So you want to keep it not very deep. So it's about 1 meter. And therefore, if the depth is about 1 meter, of course, the area, the transversal area A, which I determine in this way, is equal to the width of the sand trap times, I'm not sure whether W is the symbol that I used there. Sorry for that. If it's different, don't get impressed. Let's indicate here with the W the width of the sand trap times the depth D. And therefore the depth is about 1 meter. 1 meter. And therefore you get the estimate of A from there, and therefore you get an estimate of W. What is an order of magnitude for W? Let's say from 2 to 10 meters, usually. And then we have to design the length of the sand trap. So, how to design it? Let me make one thing, because the screen is disturbing now. I'm taking more than expected for the lecture. Please forgive me, and of course we will have to okay. Still, it's not a good okay. It's a bit blue, but I think it's better than before. Let me say, no, I don't like it. I don't like it, just a second. This way it should work, it should be everything black. Yeah, this is much better. Okay, so let me make a sketch of the center in order to clarify how to estimate its length. So this is a center. So basically we have the weir. Here we have the gravel trap, and we have the weir here. And we said that the weir is about 50 centimeters. So 50 centimeters, okay? And then we have the water into the center here. Which is about it's about 1 meter. And then downstream we have the other weir, which brings into the tank. Here we have the tank. Okay, this is our situation. So the tank is like this, and then we have water up to here. Okay, good. Now, let's suppose that at the entrance of the central we have a particle of sediment that is located here. And the diameter is d. This diameter is prescribed by the producer of the machinery downstream. We already talked about it. What we want to make sure is that the central is long enough to get this particle of water to collapse to the bottom of the central before the end of the central. And you know the velocity of the flow v here. So, the distance, the vertical distance that the particle should cover to reach the bottom is about 1 meter. Okay? And the particle has a vertical velocity, sedimentation velocity, which we indicate with Ws. So, what is the time required by this particle to reach the bottom? The time is equal to, let's say, about 1 meter divided by the Ws. Ws is unknown. Let's suppose that we know Ws. Then the particle during this time walks for a longitudinal distance moves forward with the same velocity of the flow. Let's suppose that the particle moves forward with the same velocity of the flow. Velocity of the flow we know. Therefore, we have to make sure that the length, let's indicate it with L. Not sure whether I use the symbol in the slides, but it doesn't matter. We need to design L to give enough time to the particle while it moves forward to move also vertically and to reach the bottom of the centra. So, how to estimate L? It's very simple. We know T already, so L is equal to the velocity of water V times T. Good. The only unknown here is Ws. Ws is computed with the Stokes formula. I'm quite sure that you already know Stokes formula, but in any case, if you go to my web page, there is a nice hand drawing here, which I did, that explains how to